All right. Before we start talking about solids and liquids today, I just want to recap something from yesterday that I don't think I covered when we were talking about London dispersion forces, and that was looking at something like two molecules that have the same molecular mass but look different. So let's say we have pentane. This is pentane, okay? So that's got a particular formula. If we were to have an isomer of pentane, where it's just a rearrangement of the same exact atoms, and do something like this, CH, C, CH3, CH3, this is exactly the same number of C's and H's. So they have the same formula, so they have the same mass, so they have the same number of electrons, okay? If we're talking about intermolecular forces, one thing I can tell you is these two things have very different melting and boiling points. So they have very different intermolecular forces and strength of intermolecular forces. So my question to you is, what is the primary intermolecular force in both of these? London dispersion, correct, because these are nonpolar molecules. So the question then is, why are they different? If they're the same mass and they have the same number of electrons, anyone want to tell me which one they think has a higher or a stronger intermolecular force, a higher boiling point? The pentane. Yes, the pentane does, and it has to do with the shape of that electron cloud. If you look at this electron cloud and think about it versus this, do we see why this has more surface area, right? So in terms of polarizability, our shifting capacity is a lot greater. So we can get, whoa, where did it happen to that? So we can get a lot bigger, a bigger charge difference, a bigger difference in separation. Does that make sense? So this cloud is more polarizable. This cloud, if you think about it, it's just like, there's not a lot of place to shift compared to this. So based on the surface area, the more surface area the molecule has, the more polarizable, the higher the intermolecular force. Okay? All right, let's move on to today's lesson. Today we're talking about liquids and solids. Liquids, we're going to just scratch the surface on liquids, no big deal. There are some characteristics of liquids that make liquids interesting. We know liquids, they are low compressibility, they lack rigidity, and they're very high density compared to gases. They change with the shape of the container, right? A characteristic that we often see in liquids is called surface tension. Does anybody know what that is? What that looks like? What in your life is a proof of surface tension, Ira? Yeah, when an insect walks on water due to the surface tension. Anything else? Yep, exactly. When you fill a cup, you can fill it up kind of past the top and it won't flow over. So surface tension is very common, and liquids that have super high intermolecular forces are going to have a higher surface tension. That being, in the case of water, it has a super high surface tension. Okay. Capillary action. How many of y'all have given blood? Have you seen when they check that iron test, they prick your finger and then put the little capillary tube, and the water just ding, or the blood goes up the sides, goes into the tube? That's because of adhesive forces, which I'm going to talk about on the next slide. That blood is attracted to the side of the glass container. So capillary action is due to adhesive and cohesive forces because they kind of alternate. So the liquid's attracted to the side, and then it's attracted to itself, and no, it's attracted to the side, and so it kind of goes back and forth and goes up the tube. And the tube in capillary action has to be super thin. A real thick tube wouldn't work. Okay. Viscosity. Have you all heard of that before? Every time I go change my oil, they're like, which viscosity of oil do you want? Has to do with the thickness, right? So water, I know water has a strong intermolecular force, but it doesn't have a very big viscosity. Can you give me some ideas of things that have a high viscosity liquids? Syrup, honey, oil, ketchup, yeah. Ketchup's super thick. Molasses, all that stuff. So all those things are covalent bonding and they're polar, but what makes those molecules specifically, all these examples of these sugars, is they're huge molecules. So their LDF forces are going, I guess they're not polar, they're nonpolar. Their LDF forces, no, sugar is polar because it's got OH backbone. Take it back. But there's still an incredible amount of LDF force because of the size of those molecules. So all those big fat molecules are going to create large amounts of viscosity. So this is an example of why meniscuses form. At the top is what we call a convex meniscus. We haven't seen this because we don't play with mercury. I used to when I was young, and it explains a lot of why I'm crazy now. But mercury, when you put it into a tube, actually has an inverted meniscus, while water, we know, has what we call a concave meniscus. So know the difference between convex and concave. This is just caved in. And the reason this is because glass has polar characteristics. So water, if you look at these water molecules down here, they are attracted, due to their hydrogen bonding, to the sides of the glass. So they're going to kind of creep up the side of the glass, creating that meniscus. While mercury, check it out right here, is like, I so don't like that glass. I'm nonpolar. I'm more attracted to myself than I am to the glass. So that's its way of like staying away from the glass as much as possible. So that's, I thought, pretty interesting. So moving on, I lost my arrows. Okay, so this is kind of the point of what we're doing today. We need to be able to take any solid in the world and put it into some categories. Here are our primary categories. I'm going to add a couple more, and then we're going to fill out a chart for easy access. And then we're going to answer some questions. And then I'm going to show you a little video. So let's start with the type we know the best, and that is the ionic crystals. We know ionic compounds. What makes up ionic compounds? Metals, nonmetals, metals, polyatomics, polyatomics, polyatomics. All those things are ionic crystals held together through electrostatic interaction, lattice energy. They have high melting points. Have you ever tried to melt salt? Impossible. Are frequently soluble in water. We know from our list of solubility rules which ones are and are not soluble in water. And they can conduct electricity in aqueous and molten states. So you need to know that. Okay? Questions on the ionics? What's so interesting, Noah, on your phone? Yeah, Covalent solids. Give me an example of a covalent solid. Go for it. What? Butter's a covalent solid. These fats, these are triglycerides. They're covalent solids, all nonmetals, carbons, oxygens. Go ahead. Graphite, no. Graphite's a different, it's a different category because it's special. But we'll get to graphite. Yeah, sugar, okay? Any of those nonmetal combinations, all your organic substances, those are all covalent solids. These will tend to have lower melting points. We can melt sugar. We can melt butter. Oil is not even solid at room temperature. Crisco, the waxes, paraffin, all these different things all fall into this category. I don't really like the statement they are frequently not soluble in water. I think it's 50-50. We got a lot of compounds like sugar, certain alcohols. All these covalently bond things are soluble in water. So I don't tend to agree with that statement, but the waxes and the triglycerides, those are all nonpolar and not soluble in water. One thing is totally true, though, is they do not conduct electricity. There's no ion source, so it can't conduct electricity at all. Now we get to network covalent, and this is what Rui brought up when he brought up graphite. So there's two primary ones that they focus on the AP that you might see. Carbon, as a system by itself, will take many, many forms, depending upon how it bonds. Carbon has the ability to three-dimensionally bond with itself over and over and over and over again. So depending upon what that organization is going to make totally different things. This is diamond, And I'm going to show you on the next slide. You'll see what graphite looks like. Diamonds is just carbons bonded to each other. So it's not a lone atom. Carbon doesn't sit by itself and hang out like phosphorus or sulfur does. It actually bonds with other carbons in a way that we don't normally see. Also, anything containing silicon, silicon dioxide, sand, computer chips, all these different things have these compounds in them. Silicon dioxide is what basically sand is. It's in glass. The version of it is glass. And it will three-dimensionally make crazy covalent bonded structures. So that's very special and very specific. These things are super strong. And they have super high melting points. They're not soluble in water. And they do not conduct electricity because they're covalent. There's no ions. Okay? So those are a very special category. And then the last one on this list, metallic solids. So any metal by itself, you can have lone atoms like iron, like copper, like whatever. They have high melting points, and we're going to watch a video on this. They're not soluble in water, and they can conduct electricity. You guys did the POGL. Why is all this possible with metallic solids? Sea of electrons. What I want you to use the term, the electrons are delocalized. Right? So basically, if you've got iron, you have your iron nucleus and core electrons, so it would be like iron plus 3. And the valence electrons will be shared among all the irons. So if there's 3 valence electrons for each, those are delocalized and can just go everywhere. And the video will talk about the attraction and why this stuff is malleable. What does it mean to be malleable? You can pound it into sheets. Ductile. What does it mean to be ductile? Pull into wires. And it's because of this sea electrons that allows for that play and movement of the atoms. Now, the only other category which is on the chart when we deal with lone atoms, when we have lone atoms that are the nonmetals, we can have lone atoms that are metals. Those go through metallic bonding. But we also have a whole bunch of nonmetals that don't form bonds, that just chill, like sulfur, like phosphorus. Those things are all attracted by how? By sulfur and phosphorus. What keeps these guys solid? They don't bond three-dimensionally like a covalent network. Sulfur is a yellow powder. You have white phosphorus and red phosphorus. What's the intermolecular force? London dispersion. So these are all held together by London dispersion forces. Because of that, these have low melting points. These have, they're not soluble in water because they definitely can. They definitely don't conduct electricity. There's no source of ions there. So here's some pictures of some things. I'm going to breeze through a lot of this stuff. These are examples of graphite and diamond. Both are carbons. Both are network structures. Diamond, you already saw, was three-dimensionally attached. I think graphite's super cool. So graphite is bonded in these hexagonal attachments in these sheets, right? How are these sheets attracted to each other, do you think? London dispersion forces, right? These are weak. So when you write with your pencil on a piece of paper, you're breaking that, or you're overcoming that intermolecular force. So you're writing, the sheets are coming off onto the paper, and you're not breaking these bonds, you're overcoming those intermolecular forces between the sheets. It's very cool. This talks about the pi orbital system, and this is something, you know that if you have unhybridized p's, okay, that you're going to be, each of these are only really bonded to 2 other carbons. So there's 2 unhybridized p's on every single carbon. And when they make this arrangement, you get these crazy resonance options, which basically makes this stuff really strong. These bonds are really strong, and then the sheets are in between, and that's what, when you write, it comes off onto the paper. So that is graphite. Ceramics, carbon and silicon, if you're interested, they're used primarily in ceramics when they talk about putting stuff in the kiln. that high temperature stuff, again, super, super strong bonds in these. Semiconductors, I'm not going to talk about. There are some questions in your homework. Just look on the paper. You'll be able to figure out the answers to the questions. But I'm not giving you semiconductor questions on the test. Okay, so just be aware of that. This is mainly do it for your homework. I want you to have some sort of life knowledge of this because it might come up someday, and it'll be nice for you to be somewhat literate in the area. One other thing about metals, we know that normally metals have this sea of electrons, but do you realize we can have solutions that are solids? We don't think about solids being solutions, but they are. Steel and brass are solutions. So you've got two different metals that are mixed. So it's a solid, still undergoing metallic bonding, but it's not necessarily just one type of metal. It could be multiple metals. Okay? All right. So now we're going to fill this chart in. These are our different categories. You can have lone atoms that do crazy different things, and then you have molecules, and you have lattices, ionics. So give me some examples of a covalent network. There's only two we care about. Carbon and silicon-containing stuff. Okay, SiO2, Si. If you see Si, it is going to make a covalent network. It's very specific. Give me some metallic examples. Not hard. You've got a bazillion to choose from. Thank you. All right. Thanks, y'all. That was exciting. Lone atoms, things that aren't metals but can exist as solids by themselves, just hanging out. Sulfur, phosphorus, selenium. Those will do that. Give me an example of nonmetals or molecular substances, meaning covalent substances. I don't know the formula for butter. Oh, that was a good one. Nice. Ice. Yeah. So a lot of substances, if we freeze them, things that are normally liquids, we're like, that's not, or like methane, CH4. Yeah, that's a gas, but theoretically we could freeze it and make it a covalent solid. All right, what about some salts? Let's be creative. Do not tell me NaCl. SRF, is that the formula? No, FRF. Oh, FRF. What FRF? Oh, francium. I thought you meant F and then RF. I was like, what? Francium fluoride, the thing we're afraid of. That's good. Yeah, the most ionic of the ionics. Calcium carbonate. I mean, any. And then don't forget, we have like ammonium nitrate, which has no metals in it, but it's got two polyatomics, so it's still ionically bound. Okay. Within the polyatomics, they're covalently bound, but the attraction of these two ions is ionic. All right, so now let's go through, and when I say type of bonding or intermolecular attraction, I'm asking you what makes it solid. So saying, oh, bonds, well, it depends. So covalent network, what's making it a solid network? Bond. That's bond. The answer to that is bonds. Three-dimensional, 3D bonding, 3D covalent bonding. So we get these lattice-looking things, but remember, they're not going to conduct electricity because there's no ion source. So some typical properties of these things. What are some? High melting point. They do not, no E, I'm going to put no electrons for no electricity. They do not conduct electricity. Are they soluble? Usually not. Not soluble. That would be bad. People buying these expensive diamonds, that would be really bad. Okay. Metallic stuff. What is making metals stay together and have the property of metals? The metallic bonding. Some people say metallic bonding, but I heard sea of electrons. That's kind of a Chem 1 answer. I'd rather you say delocalized. I got to respell this. Delocalized electrons. Does everyone understand what that means? An electron may be next to an atom 5 atoms down. They're not localized. They're not stuck in the same spot. Delocalized electrons, sea of electrons. What are some properties of metals? Conduct electricity, so yes to electricity. Are these soluble? Nope, not soluble. They are malleable. We got ductility. Now, people will sometimes say, oh, metals are hard. Not necessarily. Has anyone seen or touched like real gold, like 21 karat, 14, beyond 14, 18 karat gold? It's super soft. My mom has these bangles. I'm like, why the heck did they make these? Because they're like, you can squeeze them and break them. I'm like, I'm not going to wear that. That's crazy. So yeah, super, super soft in those cases. And that's just because of they have particularly large amount of electrons in their sea, making it more kind of squishy. All right, lone atoms. What keeps sulfur as a white powder? What intermolecular force keeps that? Because there's no bonding going on there. It's just a lone atom. It's not bonding to anything. Yep, LDS. And these are going to have low melting points. These, oh, and I know metals have pretty high melting points, by the way. I know I'm missing things, but this chart is kind of already filled in for you on the next page, so you have a double reference. I gave that to you in case I forgot stuff like that. Low melting points, they are not going to conduct electricity, no electricity. They're not very soluble. A lot of times they stink because they have such small intermolecular forces, they vaporize very easily at room temperature. You set a jar of sulfur in the back of the room, by the end of the day, we all can smell it. That's because it's got very low intermolecular forces, very weak intermolecular forces. All right, molecular stuff. What is keeping these? Now, we're going to have a variance of these because remember we have this sugar here, but then there's also the whole butter, wax, paraffin category. So we kind of have two situations of keeping these as solids. What are keeping these as solids? Don't say bonds. Bonds aren't keeping them as solids. Bond, if we have one molecule, we have bonds. What's keeping all those molecules arranged in solid form? Intermolecular forces. Which ones? In sugar, which ones? Hydrogen bonding and dipole-dipole. So if the molecules are polar, it's going to be H bond and dipole-dipole. If the molecule is nonpolar, it'll be LDFs. And so you've seen Crisco. You see how easily it melts, right? That's because those triglycerides, those fatty acids, have are nonpolar and have very low melting points. All right, and then, there we go. Depending on well, no, even sugar has a pretty low melting point. These are characterized by low melting points, 50-50 solubility, depends on, whatever, but no electrons, no ions, no electricity can be conducted in any of these because there's no source of ions. And the last one, ionics. What's keeping ionics together? Yeah, our lattice energy. You can say ionic bonds, but it's really lattice energy or an electrostatic attraction. And again, any bond is going to be stronger than any intermolecular force. You don't compare. They're not comparable. So don't ever think that ionic bonds are weaker than hydrogen bonding. No, ionic bonds are flippin' strong. Biology, and I don't think they teach this, but I know it's in the Campbell textbook, they say that ionic bonds are weak because they dissolve in water. No, they're not weak. If I were to try to break an ionic bond and break a covalent bond, ionic bond is much smaller. What's the reason ionic substances dissolve in water? Yeah. The polar water sneaks in, right? And then the ions are still now attracted. They're just attracted now to the sides of the water that are polar as opposed to each other. Doesn't change the bond strength. Properties of these are hard as heck. What happens when you hit an ionic compound? Does it do what metals do? No. It shatters, right? It breaks. So these are brittle. And then the video I'm about to show you shows you why. It's really cool to see why metals are malleable, but why these guys are brittle, and you'll see based on the lattice. It's very interesting. High melting points, and these are usually soluble in water. And then, I'm not going to write this down, but when do these conduct electricity? In two situations. Molten or aqueous, when it's dissolved in water. Okay, so let's do our last little practice here. This is the filled-in table. What time do we get out of here so I don't go over? 10:04. Oh no, we're not going to be able to watch the video. Okay, we're going to hurry because I really want you to see the video. So we're going to go through and just put this in the category it belongs. What column on that previous chart would you put them in? O2? Nope. Lone atom. H2S. Molecular or covalent? Yeah, molecular. Ag? No. It's metallic. Yeah, you got cut. KCl? Ionic. Si. Covalent network. Aluminum sulfate. Ionic. Neon. That's lone atom. Silicon dioxide. Covalent network. Ammonia. Molecular. Magnesium oxide. Sodium hydroxide. Methane. Molecular. All right, and so here, this is kind of fun. Let's categorize these. The first one has a high melting point, high boiling point, not soluble in water, good conductivity as a solid and a liquid. Yeah, I'm going to go for metallic here. All right. Comparably, this next one, low melting points, not soluble in water, and do not conduct anything. Molecular. The next one, pretty high melting point, soluble in water. The solid doesn't conduct, but it conducts as a liquid. Ionic. And then this last one, freaking ridiculously high melting points. The boiling point is 98,500. Not soluble in water and does not conduct electricity. This is the covalent network, yeah. It's on steroids or something. All right. So homework due. I'm going to turn the video on. We'll have just enough time to watch it.